Thank you everyone for coming to this UK SPS talk. Today it's my pleasure to introduce Dr. Bo Li, who is assistant professor in the Department of Computer Science at UIUC. She is the recipient of the MIT Technology Review TR35 Award, Sloan Research Fellowship, NSF Career Award, Intel Rising Star Award, Symantec Research Lab Fellowship, Rising Star Award, and also research awards from tech companies like Amazon, Facebook, Intel, and IBM. She also received several Best Paper Awards at top machine learning and security conferences. Her research focuses on both theoretical and practical aspects of trustworthy machine learning, security, and privacy and game theory. She has designed several scalable frameworks for robust machine learning and privacy-preserving data publishing systems. Her work has been featured by major publications and media, such as Nature, Wired, and Fortune, and New York Times. So now I pass the stage to you, Paul.
Okay, thank you, Chang, for the great introduction. So hello everyone, it's a great honor to be able to share my research on trustworthy machine learning from some perspectives such as robustness, privacy, and generalization, as well as their interconnections with everyone. So my name is Bo Li, and I'm from UIUC. So first of all, I think I don't need to emphasize too much about how popular and important machine learning models are for like our daily life. For example, autonomous driving, intelligent medical treatment, healthcare, smart city, etc., especially for some security domains as well, such as malware classification or biometric recognition systems. They have been all like almost everywhere to protect both personal and business information. However, we can see that even such very powerful and efficient, effective machine learning or AI techniques also bring us a lot of security and privacy concerns. This is one of my favorite example in real world, because whenever you do robustness security about machine learning, people may want to ask like whether it is too early to worry about it, right? Like has anything happened in real world yet about such a security or privacy problem about machine learning? And here is actually one real world example, which is in 2016, the Associated Press Twitter account was hacked via phishing emails, spreading the rumor that the White House has been attacked, which actually triggered the autonomous trading bot to dump a large amount within seconds and swap about $136 billion within seconds, which is so-called, like we know, the fake news attack, and has really happened in real world and caused certain severe consequences. And similarly, from the privacy perspective, that like the Australia airport has developed the safety screening based on the biometric recognition systems, which lead to a lot of privacy concerns about database leakage, data violation, etc., etc. So we can see that even though we are living in an actually very friendly and nice world with a lot of scalable, efficient machine learning developed tools, platforms for us to develop different algorithms, analyze different types of data, etc., which is very lucky, but still we are living in an adversarial environment, I would say. So a typical machine learner still have a very hard life to make, say, machine learning models or pipelines secure or safe or trustworthy. So I believe that's why we want to get together here and in the recent research to like explore different adversarial strategies and try to understand the adversarial world, and therefore try to develop and design robust and trustworthy machine learning techniques. So with that, given the overview, for about what we do is that in our lab, we focus on design and certify different robust, private, and explainable machine learning paradigms for real-world application. For example, taking this as a simple machine learning pipeline with from the input to pre-processing and model optimization and post-processing to the end of the output prediction or decision makings, right? There are different components here leading to the trustworthy machine learning research. Like first, about different types of adversarial attacks, which can happen in both testing and training time, right? And the physical and digital world. And therefore, based on such attacks, we and different literatures actually develop the so-called robustness algorithms or defenses or different machine learning certifications from both the feature level and post-processing level and some from model optimization level. And of course, we want to understand better about what happens inside the machine learning black box optimization. So we actually have efficient algorithms to provide log n times Shapley value calculation to understand and debug the data from the machine learning perspective to see if something happens. For example, if you have low accuracy, which data point in the training set is can be attributed to, and we should trace back to that. And in the end, similarly for privacy, there are different ways to perform different privacy attack, including different membership, different model inversion, as well as corresponding defenses. So all these things seems a lot of pieces of work. And of course, I cannot cover all in this talk, and I will mainly talk from the robustness and privacy perspective. But we may want to ask one question, right? With so many different work and publications, so if we get to ask one question about trustworthy machine learning, right? Like what's exactly the core problem we want to tackle about trustworthy machine learning? What would that be, right? So to me, from my personal understanding about trustworthy machine learning, I think in the end of the day, or fundamentally, we just really want to solve this trustworthiness gap between distribution shift or distribution manipulation. That's one fundamental question, I think, in any aspects of trustworthy machine learning. For example, from the robustness perspective, it's exactly the distribution manipulation from the adversarial perspective, which means we know that during traditional machine learning, we usually assume the training and testing data distribution are from similar, even the same distribution, right? Therefore, we can train on one and make inference on the other. However, when there is an attacker, they can come in and manipulate either of the distribution. For example, if the attacker manipulates the testing time distribution, it is so-called the evasion attack or test time attack. For example, if you have a malware, like software well-trained on your computer, but during the testing time, the attacker can easily manipulate some binaries, malware binaries, and send to your computer so that it can bypass the malware classification, but still do harm to your computer. So that is one type of evasion attack, right? And similarly, the attacker can also manipulate the training time distribution, which lead to a so-called poisoning attack, backdoor attack, or different types of names, which is also very common. For example, you can, in the recommendation systems, like in Yelp or Netflix, you can create a fake account and add fake news and etc., which will lead to the training data pollution, and then the model will be manipulated. So this is exactly from the robustness perspective, either training or testing distribution can be manipulated, and we hope the prediction or the machine learning model can learn under such a worst case distribution manipulation. And similarly, from the privacy perspective, still like originated from this trustworthiness gap from distribution drift. Essentially, we want to infer the distribution information during the testing time by querying the machine learning model or by probing different types of signals, right? So that therefore we have different types of privacy attacks and the corresponding privacy defenses from both privacy preserving like data generative models, which is more flexible for different downstream tasks, or a specific privacy preserving learning algorithms, which will be tighter for if you know what algorithm you want to train in terms of the privacy guarantee, right? And last but not the least is the generalization. I would say both robustness and privacy are the distribution drifting or the inference in the adversarial environment. And here in the generalization, we are focusing on still the distribution drift, but in a natural scenario. Like we have data evolving, we have data like changing over the time. Therefore, there are different types of generalization issues and the generalizable algorithms as well. It just cares about rather the not worst case, but the like natural scenarios. And I would say these three pillars actually mainly like develop the core component or the fundamental algorithms inside trustworthy machine learning. But also we have other like types of things like fairness, toxicity from natural language models, like other types of like explanation, etc., etc. And I really want to say is that these three pillars are not independent. They actually have strong connections with each other. And I do believe that when we can like recover the fundamental connections between them, we can actually leverage the development or the advances from one to help the other rather than reinventing the wheels. And all the other perspectives like fairness and explanations, etc., can actually benefit from the research and the result that we understand under this core component as well. For example, we know that a private model would be smooth, right? And you can imagine if a model satisfies some privacy, it will lead to such benefits of robustness. Vice versa, like a more generalized model will be more robust and also lead to some privacy advantages. So we actually have some proofs saying that if you satisfy epsilon delta privacy, you will implicitly lead to certain robustness as a function, a lower bound of the accuracy as a function of epsilon delta, etc. So I think this, if we can like recover or like uncover the underlying fundamental connections between like among all these components, it will lead to a lot of interesting findings and fundamental research. So in this talk, I will mainly focus on privacy, and if we have time, I will touch to a little bit, focus on robustness, and if we have time, we'll touch a little bit about privacy, and hopefully can give more detailed examples and explanations about this figure. So from the robustness perspective, we all know, I believe almost everyone have seen such real like adversary examples, which come from like a 2D digital world, that if you have some images and you add a small magnitude of perturbation, you will be able to mislead the machine learning model to classify such instance into an arbitrary adversarial target with very high confidence, which is quite dangerous actually. And such a in digital world adversary example can also lead to a lot of physical adversary attacks as well. And I will give some examples, and we will mainly focus on the defense perspective in this talk. So from the digital perspective, taking the autonomous driving as an example, which is one of the most popular machine learning application nowadays. And here is some examples from the physical world. Maybe you have, some of you have seen some examples here, which means on the stop signs, we can add some stickers serve as physical attacks onto it, and we on purpose do not cover the letters, otherwise it will fool human as well. So the goal here is that you cannot fool human, but the machine learning model will be attacked in such a way. So different columns here show different types of perturbation, like this looks like a fading out, and this just some stickers, white and black, but surprisingly, they are very effective in terms of attack. And of course, the positions and the sizes need to be optimized. And the different rows show different conditions, like different angles and distances, etc. And we can see all the stop signs on these slides can be misrecognized as a speed limit sign 45 by the physical machine learning classifier. And the right turn sign can be misrecognized as a stop sign. So that you can imagine will lead to severe consequences in real world if a car will never stop at such a sign, right? And previously, as some static examples, here we want to show some dynamic example where you can drive the car towards the sign. And on the left-hand side, it's a manipulated sign, and on the right-hand side, it's a control experiment. And you can see that from the captions, this, even though the car is keep driving toward this sign, the left-hand side keep be misrecognized as a speed limit sign, and the right-hand side in the control experiment, it's still the correct one. And similarly, in another experiment, we can see this is continuous, and this is a fading out example, and actually it has consistently attack as well, even under different driving scenarios. So after this example, actually a lot of people are interested and ask some interesting question. One of them is that, so this is a classification model, right? So what about other machine learning models? For example, object detection, semantic transformation, semantic segmentation, etc., etc. Here, we'll show another quick example about attacking the object detection to get some flavor about how powerful such physical attack could be. So that means here, this stop sign also similarly be manipulated, and this is attack the first RCN, and you can see all the rest of the object can be still correctly recognized, but only this stop sign can never be recognized unless you get to very, very close to this sign itself. For example, if you get very close, it actually recognizes the letters like the stop here so that you can recognize it. But you can see this will be too late for a car to stop, and we on purposely do not cover such letters. Until here, people may also ask some other interesting question saying, so far, all these attack, great, they can attack different types of models, but actually these are the white box attack, meaning that the attacker can access the model parameters, gradient, etc. to optimize such perturbation. So what about black box, right? What if you do not have access to the machine learning models, whether you can still attack it? And very interesting, there are different ways for black box attack, query-based, like zero query-based, etc. And there's one specific phenomenon which is very interesting called adversarial transferability, which means that if you generate such adversarial perturbation against the model A, such a perturbation will have very high probability to attack model B as well. Although such model A and B could be even trained on different data set, have different architectures, like different initialization, etc., etc. So that's very surprising, right? And we have some work to prove the lower bound and upper bound of such adversarial transferability to see what's the factors that will affect such transferability. But still, the research about adversarial transferability is still going on, which is a very interesting phenomenon. And here I want to just show an example to see how powerful such transferability could be, which is in a different scenario, but exactly the same perturbation we've seen before. We test this physical perturbation against another model, which is YOLO here. And when we get close to it, we can see still this stop sign will be attacked and we cannot recognize it until we get very close to it, which is too slow, too close for a car to stop. Yeah, very interesting. Actually, this road sign currently is exhibited in the Science Museum of London. Maybe some of you get a chance to see it. I haven't seen it yet. These are the pictures taken by the people who put there and send me some pictures. I think it's very interesting, and which also raised the concern that how severe such attack could be, and we should indeed worry about the security and privacy problems of machine learning before they can be largely developed for safety critical applications. So after this, people may still ask that, okay, such a stop sign is a planar object, right, with relatively 2D properties. So you can attack camera. So whether it's possible to attack other sensors within autonomous driving, for example, LiDARs and radars, and also even the sensor fusion systems. So I will show some examples just to show how powerful the attack could be, and we will go to focus on detail about the defense. I will now show the detail about how to generate these attacks. And if you are interested, we can discuss more about it. So this is an example of this autonomous driving and the LiDAR systems. We actually tested on the Apollo open source autonomous driving platform, which really I want to show here is that such a LiDAR system is not an end-to-end differentiable machine learning model only. It's a different, like contains different components. It's a long pipeline with different structures, etc., etc. So even such a relatively like complicated pipeline can still be attacked effectively, which is surprising. So you can see here with like a real world LiDAR systems, we actually put this object optimized, like this object is optimized through the 3D point clouds. We use some 3D, say, transfer distance to control the stealthiness of such attack. And we optimize the shape and 3D print it and put on the road. And here is a control experiment with a box of similar size. And then we actually drive a car towards it. And from the LiDAR detection system, you can see this object can never be recognized, which is clearly here for human, but the car can never recognize this object, which means the car can run into it if it's an autonomous driving system. And in the control experiment, we can see this green box can always be recognized, which means that it's safe and the LiDAR systems is effective. And similarly, we can put the object onto different positions, and while we drive towards it, we still cannot recognize such a box, but in the control experiment, clearly we can see the green box here. So which shows that the LiDAR system in real world can effectively be attacked as well. And later on, there's in security, we have this long history of cat and mouse game. We have different attacks, then we have different defenses, like people develop different sensor fusion systems to defend against such attack. And then we would say that it's actually still very easy to attack such sensor fusion systems by jointly optimize the LiDARs and the camera together with different constraints in both 2D and 3D. For example, in 2D, we hope the shape will be stealthy, but still reflect the lasers so that the LiDAR will misrecognize the shape, and we also optimize the texture on top of the objects so that you will also fool the camera, right? And by joint optimize, we can see that indeed we can optimize the object look like this, which still reasonable to human, but actually when you place it in real world, it will attack a sensor fusion system. For example, this is a simulation in both like LG and Apollo, and we can see this is the optimized adversary object. And when the car driving towards it, it can never recognize this object, even with the sensor fusion system. So the car run into it. So if it's a real world testing, it will be quite dangerous. But of course, in the control experiment, the car can recognize this object and stop when it sees such object. And more examples, if you are interested, you can play online, and we have a lot of such demos on our website. And so far, there are different autonomous driving companies are aware of such attack and also try to test against it to evaluate the robustness and try to improve the robustness of the driving systems. So far, I would say we have seen and shown a lot of such attacks, and they are very effective. Hopefully, I can convince you that all the attacks, no matter in digital world and physical world, they are very effective. And no matter what types of like machine learning models, either it's classification, object detection, like even generative models, reinforcement learning, I didn't touch all the models, but I can let you know that for any models, I feel that we can always attack it without any like strong challenges. So that lead to a question, right? As the white hat people, as a good people, right? We gather together and we really hope by exploring such attacks, we can improve the robustness of machine learning models so that we can safeguard our learning systems. So here are some.
There is a question from Luca. Luca, do you want to ask the question yourself?
Sure. On your attack, you showed that on the voxel grid, you could shift the thing. Does it also work on algorithms that use the bit clouds directly without transformation to the voxel grid?
Yes, so it's only work on the voxel grid, and it's a voxel grid. It's a point cloud voxel grid, 3D voxel grid. It doesn't like project to 2D, but there are indeed some other attacks attacking from the 3D to 2D projection, and after the 2D projection, what happens there? Yes.
Thank you.
Yeah, thank you. So yeah, thanks for the interesting question. Indeed, there are different attacks like only in 3D, 2D, and the joint. Here, since we focus on sensor fusion, so we actually consider both 3D and 2D for different sensors. And of course, against such attack, how we can defend against them, right? So there are many hundreds and thousands of papers about defense, like empirically from detection and prevention perspective from over the years, like starting from 2018, I cannot like list all because more and more work are there. Therefore, we can join the effort and develop a different defense. However, I would say most of such empirical defenses so far have been attacked by additional like adaptive attackers, which have additional information or just a strong ability to attack again against such defenses. So that leads to another question that we really need some guarantees for such defense so that we can be more confident about the worst case scenarios in terms of the machine learning defenses, right? So there is a new direction of research. I would say it's rather young from, I think starting from 2017, etc., about certified robustness of machine learning, which actually aiming to give a lower bound for the accuracy under certain adversarial perturbation conditions. For example, such condition could be the L2 norm of the perturbation is bounded by something, or other LP norm is bounded, or the semantic transformation of the perturbation is bounded. So under certain conditions, we can provide a lower bound of the accuracy of the model that will serve as the certification of the machine learning model, which you can see is very good notion because now we know what will happen in the worst case, and we don't need to worry about new types of attack as long as the attack can satisfy these types of constraints. So it's a very good notion, and I really like this direction. However, there are some drawbacks and limitations as well, and we can see later. So first of all, I want to, since although it's a young direction, but since it's very interesting and important, as you can see, there are many work along this direction. So I want to give a brief categorization, which is in one of our SOK paper as well. And we also have some leaderboard online with open source toolbox. So all the algorithms in this branch, in this tree, you can easily implement it with our open source toolbox. So basically, under this robust verification, there are first two branches, complete and incomplete. Complete means you certify both, you can say false positive and false negative, meaning if given an instance, if I tell you that it can be certifiably robust, it is indeed certifiably robust. But if I tell you if it's not certifiably robust, it will be indeed not certifiably robust by definition for the completeness. But incomplete means if I tell you it's certifiably robust, it will be. But if I tell you it's not, then it could be it's not, or it could be because my model or my algorithm is too loose, so I cannot certify this instance. So it's actually a false negative, but that is less dangerous than we have a false positive, right? Therefore, the incomplete verification give the one direction of such certification. But of course, there are benefits of this. So you can see from the complete verification perspective. So overall, if we want to certify robustness, we want to solve a very complicated, expensive min-max problem, right? We will discuss later, but on the high level, the min-max we want to solve is that mean over the model parameter theta, for example, and max over delta, which is a perturbation. And the objective is a loss function of any machine learning model, for example. And you can see we actually need to solve this min-max under non-convex property of the machine learning model as an expensive constraint optimization. So in the complete verification world, we can solve it by expensive, say, mixed integer linear program or branch and bound expensive like strategies to solve it. And so far, this branch can only scale up to about 200 to 300 number of neurons, which you can see it's not as scalable as current like big networks we play with. And the incomplete one actually can scale up much larger neural networks and data set. For example, in the incomplete verification, it also can be categorized as deterministic and probabilistic. For the deterministic, we can relax such constraint optimization by linear and nonlinear SDP relaxations so that we can solve, but still they are scalable, but not rather scalable to say ImageNet types of images. Only this like probabilistic branch can actually scale to ImageNet and large data set. So after this categorization, I hope you can have some understanding about the trustworthy, like certified robustness word. And let's look at some state of art to get more flavors about this line, and we can get to one or two detailed algorithms. So far we can see on small data set, for example, MNIST, the certified robustness is about 93, and the state of art empirical robustness is about 96. So I would say this gap is not that large. So it's actually, we can say it's good on small data set like on MNIST, we can achieve very good successful certification already. But on rather like slightly larger data set like CFAR, with L infinity like this small radius, the certified robustness is about like 39%, which is the lower bound of the accuracy. But for the empirical robustness, it's actually 65, about twice larger than this. So we can see there is still some gap. And this gap attribute to either we need to like explore more powerful attacks to lower down this number to fill in this gap, or we can develop more effective certification method to further improve this number to fill in this gap. And to me, I believe there are more like effective and advanced certification method to further improve this certification so that we can fill in this gap more effectively. And this looks okay, but you can see if on large data set, for example, ImageNet, the certification is super low and it's almost not practical for real world usage. So that means along this line, there are still a lot of open questions and directions that we can explore to provide higher certification for large scale data set and large models to further improve the certification. And we have a leaderboard that people can check so that you can understand the current state of art on different types of models and different data set and different LP norm, different radius, etc., etc. So hope this can give an overview about the state of art, and we can see it's still very challenging to provide a usable certification for machine learning models on large data sets. So next, we want to see whether we can do something to help improve such certification, right? We can, so to me, I'm thinking either we can use some additional information, because currently all the machine learning models are, like say the pure statistical machine learning model are only focusing on the pure data-driven like properties, which some properties of the data or models have not been modeled by the data itself, right? For example, some domain knowledge, some logical inference from the human side. So we really hope that we can integrate some external information, for example, intrinsic from the like spatial or temporal consistency of the data, or the extrinsic information such as domain knowledge, etc. So one very interesting motivation is that in this year, the NIPS challenge, actually one reinforcement learning with tacit knowledge actually help in the autonomous the RL agent to achieve the top one position of the challenge, which means that the knowledge itself, extra knowledge itself, is really helpful. And that also motivates the research about the robustness, whether we can leverage some robust like domain knowledge to help improve the certification of machine learning model robustness. So here I will give one example to model and integrate the knowledge and the logical inference abilities to machine learning models as a pipeline to help improve the robustness and help improve the certification. And I believe this is one type of pipeline, and there would be different types of strategies and pipelines that we can include or integrate domain knowledge. So I hope this can inspire other interesting work from different groups. So here is one thing that in our group, we propose as the sensing reasoning pipeline, which actually integrate the sensing part and the reasoning part. So the sensing part is that, of course, we still want to leverage the expressiveness and the good representation extraction from neural networks, so that we integrate different neural networks or even other statistical machine learning model like SVM or whatever you like, as a sensing part, which takes input of the image or any real world input and given the output. And now the output will be given to a reasoning component, which can be realized by some probabilistic graphical models, for example, Markov logic networks or Bayesian networks, etc. So that this logical inference part will integrate the knowledge from some knowledge base or human constructed knowledge to build the structures and take the output of the, say, the neural network as the input and propagate to different factors. For example, in this example, we can say, oh, this node predict whether it's a dog and this node predict whether it's a cat. And we can see this factor show a dog should belong to an animal category. If we attack this node to be say a stop sign, right? And then you can, because of the knowledge, you can know the stop sign should not belong to an animal category. So this knowledge will be violated and it will try to automatically correct such a prediction. So that's the intuition of such a pipeline. And the motivation is very clear that we can see all the previous attack we have shown cannot attack human, right? But they can attack machine learning model effectively. So that means, can we integrate some human knowledge and logical inference ability such that such attack can be avoided or improved via such reasoning inference? But again, even with such, I would say, very promising sensing reasoning pipeline, it still have some obstacles. For example, the first obstacle is that for the such a probabilistic graphical model, for example, Markov logic network, the inference time is sharply complete, which is quite expensive and it's not scale up to large scale data sets for sure. But such a challenge also leads to some opportunities. For example, this family of graphical models actually can help provide nice properties from the exponential family and some functional structures for us to actually solve this min-max problem. So concretely, we can see that by building up such a sensing reasoning pipeline, which means in this example, as we discussed, there are different sensors, like to identify whether this is a dog, cat, or animals. And we develop such a logical rules, say dog belongs to an animal and the cat belongs to an animal, etc. And we log out the interface factors and train the interior factor weights. And after training the weights, we can actually calculate the accuracy of the reasoning component, and then try to calculate the lower bound and upper bound of such accuracy, so that we can certify this end-to-end machine learning sensing reasoning pipeline. So first, let's look at what we want to certify. So basically, given all the sensors in the MLM, and we actually want to calculate the accuracy as a Z1 divided by Z2. So Z1 represents in this MLM program all the correct assignment for this MLM, because all the sensors here can give you the variables which indicates the binary variables, like it's dog or not dog, like that. And to satisfy all this logic, we need some assignment. So the number of correct assignment divided by the number of all the possible words for this assignment, this is the accuracy of this program, right? This MLM program. And what we really want is to upper lower bound this value so that we can certify the accuracy of this program. But as we just discussed, to calculate the inference time or such a robustness certification is very hard. So we know there is a famous problem for counting, and we can actually write the robustness problem that we want to certify, which is the theta here is drawn from benign and adversary distribution, and we want to bound the marginal prediction probability by some value, right? And to calculate such value, we can actually reduce the counting problem to this robust problem, which means we can prove this robustness problem is Sharpie complete for either MLN or other programs, including Bayesian network and etc. But although it is hard, let's see whether we can make some small assumptions to make this happen computable in real world. So what the assumption we want to make is that, can we assume we have some oracle to the statistical inference, which is Sharpie complete, but we can assume the oracle with some noise. That means still we want to calculate the Z1 divided by Z2, and we take the log, it will be Z1 minus Z2, right? And we want to take the lower bound and upper bound of it. We can see the upper bound will be max Z1 minus mean, and vice versa, the lower bound will be mean minus the max, right? But this is hard to inference. So we can make assumption that this Z delta is through some oracle, which equals to the ground truth, which we do not have such a ground truth, plus the noise here, which represents the perturbations, and the perturbation is bounded by C, which is a magnitude that we have seen in all the previous definitions. And in such a formulation, surprisingly, we can show that it is possible to prove that when this lambda, which is the coefficient before the perturbation itself, is larger than 0, this actually the delta itself is monotonically increasing. And if the lambda is smaller than -1, we can prove that it's monotonically decreasing. And this will be proved through some like the Taylor expansion, and then we can analyze it and we can show such a monotonicity. Therefore, if it's monotonic, everything becomes easy and possible. So we can get the mean and max at the 2 points, minus C and C, right? Because it's monotonic. And if the lambda is between -1 and 0, actually we can prove it's convex, so that we can still use the 0 order to find the optimal, and then choose one of the point as the other mean and max, right? Therefore, we can actually solve this min max and upper and lower bound such marginal prediction probability. So far, it's so good, and therefore we can show such analysis can be generalized to different types of graphical models like Bayesian networks and decision trees, etc., which can integrate the knowledge. And here, let's look at an example. So this is one of the ImageNet subset called PrimateNet, which the goal is to classify all these different types of monkeys. And there are different types of structures. And we only use two types of knowledge within such a structure. For example, the knowledge is, one is hierarchy, which means if it's grade a pay, it definitely should belongs to a pay, right? And the other types is exclusive knowledge, which means if you are grade a pay, you are not lesser pay because you can be only one of it. So, and we can represent such a knowledge into the first order logic, and we can easily embed such a first order logic into the Markov logic networks, right? And within such embedding, and we can build up the sensing reasoning pipeline as we discussed before, and we can see some result with such knowledge integration. So the interesting thing we can see here is that after such knowledge integration, the benign accuracy actually didn't drop and even increase a little bit, which is very interesting because we know there should be a trade-off between robustness and the benign accuracy, right? But since we add additional signals, additional information, such as domain knowledge, not only the benign accuracy improve a little bit, but also the certification of the robustness dramatically increases. For example, here with knowledge and without knowledge, and such a sigma just to show the smooth parameter of the model. So we know in the state of art, compared with single neural network, we need to smooth the neural network by adding some Gaussian noise so that the model can be smooth and robust, and we can compare with the state-of-art single neural network certification under different smoothing parameters and with different ratios of number of sensors that we attack. And we can see such certified robustness improves like almost twice compared with the standard certification without any knowledge integration. So that's a quite significant improvement in terms of certification on robustness, which is quite promising. And not only for images, but also for other types of data like NLP. This is a task for stock price prediction, and the prediction is drawn from the like news, stock like company news from collected from Twitter and other places. And the knowledge we use is that the open and closing price of the stock should add up together with the the increase and decreasing over the day. So it's an arithmetic rule. And the other knowledge we use is that if some news say the company make profits, then the stock should increase like that. So with these types of knowledge, we can see not only the robustness, but also the benign accuracy actually improves compared with standard one. And here, very interestingly, we also show that the y-axis shows the frequency of the correctness of the prediction, which actually shows the confidence. So you can see the blue bar here shows the result with knowledge integration. And the interesting thing is that not only the knowledge integration can help improve the robustness, which always show on the green part, but also it improves the confidence of such prediction, means it will always be very confident to make it robust. But of course, for some large attacks, it could be confident to go wrong as well. So this is an interesting observation, and because it's a knowledge, so the model actually is always confident. So the benefit for confident correct is that the model is more stable and it's very hard to be attacked again because of such high confidence correctness. So this is an example, and we also want to go back to the previous stop sign example to show that we can also use, previously it's a structural knowledge, and here we can also use some other common sense knowledge to improve the robustness of a sensing reasoning pipeline. So I will go brief into this example to give a little bit more flavor about how knowledge integration can help, and we can go to other part. So basically here, again, with the stop sign, right? And we can see all the attacks before. So people actually ask the question a lot like, oh, human cannot be attacked, whether we can ask the machine learning model to identify the boundaries, identify the red color, etc., to identify this stop sign. Yeah, we hope the machine learning model can do that, right? But what's the principled way to do it? It's a question to answer. Therefore, we can see here, we actually can train similarly as this sensing reasoning pipeline by having some main sensor to classify the row size, right? It's a multi-class classification. But for other, we call auxiliary sensors, they can like predicting different specific knowledge. For example, whether there's a stop pattern in it, or whether it's what's the shape of it, whether it's octagon or other shapes. And then we can see there are two types or two directions of the knowledge. One is one direction, means if you have this stop pattern inside, you will infer it should be stop sign for this main sensor prediction. And on the other hand, if it's a stop sign from this main sensor, you will definitely be octagon shape. You cannot be other shape, right? We know that. So with these types of knowledge integration, like two directions, is kind of sufficient and necessary conditions. You can view it that way, that easily we can integrate this like a conditional random field with sensing models together. And we can actually prove the lower bound of such pipeline, and also prove that this pipeline will always have higher accuracy than only a single machine learning model as a main sensor. And I will not go to detail about the proof, but the intuition is very direct, but the proof itself is a little bit tedious. So basically the proof idea is that if you can find the optimal weights for those like sensors, such that those auxiliary sensors will contribute, that their weight is not zero, right? They will not contribute optimally, not necessarily optimally, as long as they contribute, right? They are larger than zero. Then the accuracy of the whole pipeline will always be higher, and it's always can be bounded by certain lower bound. And the very interesting thing for this pipeline is we can see, similarly with our conclusion before, in terms of benign accuracy, it's increased. And in terms of against different attacks, so the x-axis here, very interestingly, show different number of attacks, like this many number of attacks, including LP bounded, white box, black box, like common corruption attack, etc., you name it. Because the nice thing for this pipeline is that it's attack agnostic, right? You don't need to know the attack like in adversarial training. You can directly build it up and test it against different attacks. So it doesn't need to know the attack properties or the types, so that if you evaluate against different attack, like the physical attack we talked about before, right? All the like the green part show the benign accuracy increase and the robustness increase like 80% or 30%, quite significant, right? And if you evaluate under different like white box L infinity and the white box unforcing attacks like JPEG, snow, fog, all the other things, the green part show that it's always improved a lot in terms of the robustness, and sometimes the benign accuracy have some small sacrification for it. And under some common corruptions, and it's also robustness dramatically improved. And very interestingly, not only for image, but also for different like NLP, this is online, we have this like leaderboard, you can test different large NLP models, and reinforcement learning, you can also test different reinforcement learning games, and will provide you certification in terms of the lower bound of the reward and the action prediction consistency, etc., etc. And this is actually the first certification for reinforcement learning, which is in iClear this year. And if you're interested, we can discuss more about it. So which I really want to say is that certification is quite promising and rigorous, I would say, but it's still limited to certain small radius of attacks, and sometimes it's expensive. So there are a lot of room and interesting directions we can go to certify different models, different types of perturbations, etc., etc. And how to make it realistic, right? In real world, we can actually consider to, for example, in the autonomous driving scenario, because we do a lot of work in autonomous driving application and testing, we can actually use the knowledge to generate the safety critical scenarios for testing. For example, this is one type of knowledge of common sense that you can use the knowledge like the car should be on the street and the two cars should not overlap and they should have some distance between each other, etc., etc. So the node here actually can represent the positions of the vehicles to enforce such common sense knowledge so that we can efficiently generate safety critical scenarios, driving scenarios for testing. And this is one type of knowledge in real world case. And we can also use other types of knowledge, for example, the causal relationship, right? In this simple example in the cross that you have this car driving by and there are some pedestrians. So you know the pedestrian's position will be the causal relationship with the speed of the vehicles. So you integrate such a causal graph into the scenario generation pipeline, and you can leverage it to generate scenario guided by such causal relationship. So it will help you to generate safety critical scenarios very effectively and test in real world. So, okay, so far I think I go through some real world attacks and some defenses, and hopefully, again, I think this is one of the most important information I want to emphasize about the relationship between different components and different perspectives of trustworthy machine learning. And it can be rigorously certified and it can be used in real world cases, for example, autonomous driving and medical applications, etc. And they are a holistic framework, and hopefully we can explore more and understand from different pillars under this trustworthy machine learning framework. Yeah. Thank you, everyone. I think I used the time. Sorry about that. And let me know if there are questions.
Right. So if you have questions, please ask. And I will ask the first question, I guess. So when you talk about this certified robustness, and then you showed, right, with knowledge and without knowledge. When you use without knowledge, do you mean a single neural network, right?
Yes.
So my question is, would ensemble in general increase robustness? Like even if I don't have knowledge, but I have several classifiers and then I have a majority votes, would that increase robustness?
Yeah, that's a very good question. Indeed, ensemble will help and improve the robustness, and there are some work, and actually we also did a lot of work on ensemble robustness. But in general, I would say such comparison, the conclusion will still be true because the ensemble robustness certification will improve a little bit compared with single model, but the improvement is about like within 10%, I would say. But the knowledge improvement is about like you can say 40 or 30%. So it's always exists the ensemble as well. It's mainly because in ensemble model, it's great. It can leverage additional information, but not this specific knowledge and logical inference, which helps a lot for the robustness. Yeah, that's why.
Okay. And another question is, would the size of a model affect robustness?
Yes, exactly. That's a good question. So that will affect a lot, I would say. So in general, for larger models, if we do smoothing, for example, we want a model to be to certify a model, we need to smooth it. And usually when we smooth it, we need to enlarge the model size to smooth. Otherwise, it won't have good enough effects. So we usually double the size of things. For example, even when we do adversarial training, we also enlarge the size and then do adversarial training to achieve desirable robustness. So I would say in general, larger models can help improve robustness, but there are also, on the other hand, some literatures to explore if we do model pruning, whether the pruning can help robustness as well. And there, in this line of research also achieves some successfulness. So I would say there could be some key neurons, like stable neurons or like effective neurons that help the robustness, but just if it's a very small model, we cannot find them. So if you first enlarge them and then pruning, maybe you can find those effective neurons. I think that's my understanding about this like line of research.
Okay,
Yeah.
so a follow-up question. If you enlarge the network size, then would that cause worse overfitting and then affect privacy?
That's a good point. It may or may not, I would say. May means, as you said, if the model is large, it can indeed memorize training data better. So it may lead to privacy problem. However, with a large model, when we want to enhance the robustness, we usually need to like regularize a model, like to be smooth, to satisfy some properties like malicious or some smoothness, etc. So these types of property you can see actually help robustness, help privacy, and therefore it can also benefit some robustness privacy. So indeed, these types of trade-off and the integration is very interesting. I think we actually proved private model could induce certain robustness, but we didn't prove the other way direction. So I think that's an interesting thing to explore as well. Yeah.
Okay. Yeah.
Yeah.
Okay. So there are several questions in the chat. Let me see.
Oh, very interesting. There's one question say, have we tried the attack on state of our face recognition data set? Definitely. Very good question. And we tried several work, and we mainly focus on the black box attack in that setting. And we have one SML and last year CVPR about it, which means we want to reduce the number of queries and attack the face recognition systems. And we end up, the result is that we are able to attack the public API, which we have no idea about the model, and with a small amount, like 100 of queries to query it and effectively attack the face recognition to be arbitrary, whatever face we want. So it's very effective, I would say, in terms of the attack. Yeah, let me know if there are more questions about it. And the second question is, does the size of the model indicate the number of parameters the model has? Yes. So the size of the model indicates the number of parameters as well as the complexity. So basically, first of all, the parameters will definitely be increased and the complexity will be increased, but usually as we discussed, we want some good properties of the model so that it can satisfy good robustness property. Therefore, we need to smooth it, which means the complexity or the expressiveness could be, relatively reduced or things, but not much. We still hope to have a large expressiveness of the model, yeah, to be able to work in the worst case scenario. There is another question, say the trade-off between different perspectives interesting, robustness, privacy, and performance. I'm wondering what approaches that you have explored, thoughts about that. Oh, that's a good question. So I explored several and still ongoing. So for example, so as I said, from the federated learning perspective, we have one paper showing that because federated learning already satisfies epsilon delta DP, that's the goal of federated learning, right? So we prove you can get robustness for free if you have epsilon delta. So the robustness is in terms of lower bound of like prediction consistency, which is a lower bound of accuracy, and the attack cost. So we also want to upper bound the attack cost as one type of certification. So in terms of these two type of certification, we can prove if you satisfy differential privacy, you can achieve the robustness as a function of epsilon delta. And we didn't explore this like robustness to privacy yet. And from privacy to generalization, we haven't yet, but for generalization to robustness, we explore some, for example, we prove that, actually from robustness and generalization, we prove both directions. That is, if the model is adversarial transferable, right? And another transferability is domain transferability or knowledge transferability, which is like focusing on the generalization. So we prove these two transferability are bidirectional indicator for each other, which means if two models are more adversarial transferable, they are more domain generalizable or transferable as well, vice versa. So these two connections we explored, but not much this direction yet. So I think there are some interesting connections we can explore further. Yeah, thank you for the interesting question.
Okay,